Sampling techniques. In the sampling technique, we'll have the three types of techniques. The first one is instantaneous sampling. There is a general sampling what we have seen in the process of sampling theorem. That is, we have taken an initial signal of x of t and it is being multiplied with the train of impulses function and the output as some y of t, right? That's y of t is simply multiplication of the x of t and the train of impulses function. Basically, this x of t can be any continuous signal like this, any continuous signal x of t and the train of impulses function which is been like this. Now this is a continuous signal where it is been defined for all the values of the t. We can take any continuous signal here. Next, the signal is the train of impulses signal, where this train of impulses will be defined at t is equal to 0, it will have a one impulse. At t is equal to ts, will have another impulse. At t is equal to 2ts, will have another impulse. At 3 is equal to 3ts, another impulse, and so on. And in the negative side also, we'll have impulses at minus ts, minus 2ts, and the minus 3ts, and so on. This is the train of impulses. This will be multiplied with our continuous signal. Therefore, we'll get the output y of t as x of t into train of impulses function. That means when we plot this y of t graph, first at t is equal to 0, initially at t is equal to 0, here the value is 0. That 0 into impulse function will get the output as 0. Next, at t is equal to ts, this particular sample will be multiplied with the value at here. Therefore, we'll get a one particular impulse. Again at 2ts, this particular impulse and the value at here will be multiplied. Therefore, we'll get another impulse like that at 2ts. Again at 3ts. Again at 4ts, 5ts, 6ts, 7ts, 8ts, 9ts, 10ts. Like that. For every values of the ts, then we'll get the corresponding output y of t. Generally, this y of t will be given as by the it's a multiplication of x of t and the train of impulses function. And this train of impulses function, as we know, it is always been written as summation from minus infinity to infinity delta of t minus nt, delta of t minus nt. Okay, this one, and take the corresponding Fourier transform of the entire thing. Therefore, we'll get the expression as being equal to y of omega is equal to, it is 1 by t summation n varies from minus infinity to infinity x of omega minus n omega s. This already we have seen the derivation in our sampling process or the sampling theorem. The same process is nothing but this instantaneous sampling. This instantaneous sampling is also known as our ideal sampling, is also known as the ideal sampling, where in this ideal sampling, why it is being called as an ideal sampling means here the duration of the impulse is being very less. That is the tau tends towards 0. The duration of the impulse signal is being 0. That the tau tends to 0, ideal impulse, that's why it is being called as an ideal sampling. In specifically, it is also be called as an impulse sampling also. As we are using an impulse train of impulses function, it's called as an impulse sampling. As the duration of this particular impulses will be very less, that is the tau tends towards 0. Therefore, it happens only in the case of ideal case. That's why it is called as ideal sampling. And it is also be called as an instantaneous sampling, which is being defined for every instant of time. That's why it is called as an instanter. This is the first technique of our sampling process, which is ideal sampling. The next technique is nothing but our practical sampling, which is the natural sampling. We'll see it next. We'll see that one next. The next topic is the natural sampling. The natural sampling is also be called as the practical sampling. It's also be called as the practical sampling. In the practical sampling case, we'll take a simple switch connection like this. For the switch connection, we'll give the input as x of t. For the switch connection, we'll take the input as x of t, and the switch will be operated for the p of t like this. That's when the p of t is being 1, the switch will be closed. Switch is closed, and when the p of t is been 0, the switch. When the p of t is been 1, the switch will be closed. When the p of t is equal to 0, switch is said to be open. And we'll get the output like this. Basically, if we see the signals, first signal as a continuous signal, which has been like this. This is a continuous signal, and the switch will be operated for the p of t signal. When the p of t signal has 1, the switch will be closed. When the p of t signal is 0, the switch will be open. These are the waveforms for the first initial continuous signal, which varies with respect to time continuously. Next one is the p of t, which is nothing but a square waveform, which will have the square waveforms like this. And from this particular p of t, when the p of t is been 1 here, then the switch will be closed. Whenever the switch will be closed for this particular duration, then for this particular entire duration, whatever the signal that will be present will produce as our output. That's why we'll get the sampled version during this particular duration. During as the p is been 1, therefore for this particular duration, whatever the signal x of t, that will be produced as our sample, that is xs of t. Next, when the p of t has been 0, then 0 will be multiplied with the signal at here, therefore our output has been 0. Next, again when the p of t has been 1, then take that continuous signal, that will be multiplied with 1 here, therefore we'll get a continuous signal, that is nothing but our sample version. Next, again it is been 0. So here it is been 0 as because of the p of t is been also 0 here. Next, this p of t has been 1, then 1 into this particular one, therefore the continuous signal will be produced. These are the time domain waveforms, p of t, x of t, pt of t, and the sample version. Next, the corresponding frequency domain representation, that's the Fourier transform of this one. X of t is x of omega, and the Fourier transform of this particular pt of t is nothing but p of f. Again, the Fourier transform of xs of t is xs of f, that is nothing but our impulse signal. We're considering this x of omega as a band limited one initially, and p of f, as it is a square waveform, we will have a continuous impulses, will be present at a specified time intervals, like it be the TS, 2TS, 3TS and so on. That's minus TS, minus 2TS and so on. Next, for every sample at the P of F, there is a one particular spectrum in the sample version. That is for at t is equal to 0, we'll have an impulse. For this particular impulse, this spectrum will be presented here. That is, this is for x of omega, for the t has been 0 at here. Similarly, for the t is equal to ts, we have another spectrum. For t is equal to s, another spectrum. For t is equal to minus ts, another spectrum. T is equal to minus 2ts, another spectrum, like that. This is the frequency domain. According to this particular spectrum's position, that is spectrums as non-overlapping, overlapping, as well as spectrums touch each other, the sampling will be characterized into the three types as undersampling, oversampling and the critical sampling. And the critical, and for the case of the undersampling, again the aliasing occurs. To avoid that aliasing, we should take the sampling process, Fs should be greater than or equal to 2Fm. And this natural sampling is also be called as the practical sampling, because developing the square waveform with the width of tau as this much is practically possible. Therefore, practically will use this particular sampling process. That is the natural sampling or the practical sampling. The next topic is the flat top sampling. Next topic is the flat top sampling. In the flat top sampling, we'll use the two switch connections like this. The first for the S1, where as usually the x of t continuous signal will be given. And the second switch is at here, which is in parallel to the capacitor C. In parallel to the capacitor XS of t. Here it is been operated with the two switches S1 and S2. In the case 1, as that is S1 has been the S1 is closed and the S2 is open. Therefore, the diagram will appear like this with the x of t. This is S1 is closed. This one as S2 is open, and we'll have a capacitor C, and we'll have the output XS of t. Therefore, the capacitor will get charged to this particular X of t. That the capacitor will be charged to the XS of t. If you take this was a continuous signal, now if at t is equal to 0, this happens. For example, as S1 is being closed and S2 is open. Therefore, this particular capacitor will be charged to this x of t value. Therefore, our output XS of t will goes to this particular sample value. This is x of t. The capacitor will be charged to this particular value, and this particular sample will be holded for a particular duration of tau. That this process will be holded for a particular duration of tau. Next, that's generally this tau will be very less value only. Therefore, it will be holded for a particular duration of tau. Again, in the case 2, that the S1 is been open and the S2 is closed. Therefore, the circuit will appear as with the S1 as open at here and S2 as closed, and the capacitor is as this. Therefore, the capacitor will discharge through the switch S2. Therefore discharged means therefore the output will goes to 0 itself suddenly. Therefore the capacitor will be discharged to the capacitor to the switch S2. Therefore the output will goes to the 0, and the 0 will be continued as this. Again, whenever the switch S1 is being closed and the S2 is being open, again the same process repeats. That X of t will be applied to the capacitor. Therefore the capacitor will be charged to this particular X of t. Therefore the capacitor voltage will be charged here. Therefore here the particular sample will be picked and it will be held for a particular duration of tau. After holding, the second case will appear, that is S1 is open and S2 is closed. Therefore the capacitor voltage will goes to the zeros, that is by discharging through the S2 switch. Therefore it will be 0 itself. Again the same action will be repeated again for when the S1 is closed and S2 is open. Therefore again we'll pick up the one more sample and it is holded for a particular duration of tau. Then it will be maintained like that. Like that the same process repeats. That we'll take the samples at the regular intervals and it will be holded for a particular time instant. This is a sample and it will be holded for a particular duration. That's why this particular technique will also be called as the sample and hold circuit. Sample and hold circuit. Sample and hold circuit. This process of sample and hold circuit can be done by the switches here. Generally the switches that we'll use here is the FET devices, that the field effect transistors, which is used for the switches here. Initially this sampling process is also a practical sampling where the switch S1 and the S2 can be taken as an on and off for a particular durations. Therefore this is a practical used sampling where the sampling and holding process will be takes place. That the two steps will be takes place. One is the sampling and another one is the holding circuit. That's all. That is the flat top sampling or the sample and hold circuit. Thank you.